Welcome to next lesson in magnetic fields in matter. In the last class, we have finished the theory portion of this chapter. So here we will start with the problems and solutions mainly discussed in Griffith textbook and also in Purcell textbook, which is also a part of your syllabus. So first problem is, of the following materials, which would you expect to be paramagnetic and which diamagnetic? Materials are aluminum, copper chloride, carbon, lead, nitrogen, then sodium chloride, sodium, sulfur, and water. So the general rule here is the materials containing an odd number of electrons expect to be paramagnetic because they will have a non-zero spin magnetic moment. And elements or molecules or compounds with an even number of electrons are expected to be diamagnetic. Here aluminum, copper chloride and sodium all have odd number of electrons. So from the general rule, we expect them to be paramagnetic. But actually copper is slightly diamagnetic. As usually, as discussed in the chapter, it is a quantum mechanical behavior. The general rule is only approximately correct. So the rest, that is water, sulfur, nitrogen, molecule N2, etc., all of them contains even number of electrons. So they are expected to be diamagnetic in nature. Now the second problem is, at the North Pole, the Earth's magnetic field is vertical and it has a strength of 0.62 Gauss. The Earth's field at the surface and further out is approximately that of a central dipole. 1 Gauss is equal to 10 raised to minus 4 Tesla. The question is, what is the magnitude of the dipole moment in Joule per Tesla? And second question is, if we imagine the source of Earth's field as a current ring on the equator of the Earth's metallic core, the core of the Earth has a radius of 3000 km, which is about half the radius of Earth. If we assume like that, how large would the current have to be? Radius of Earth is 6371 kilometers. Here, for finding the magnitude of dipole moment, we approximate the Earth's field, the field of the Earth, as the field of a dipole at the center of the Earth. And the magnetic field at the north pole of the Earth is given as 0.62 Gauss, that is 6.2 into 10 raised to minus 5 Tesla in SI system. The component of magnetic field of a dipole are, that is the radial component is mu0 2m by 4 pi r cube into cos theta, and the component along the polar, that is d theta, polar component is mu0 m by 4 pi r cube into sin theta. Here the dipole is assumed to be lying along the north-south direction. So we can find the dipole moment of the Earth if we set the angle theta is equal to 0 for the north pole, because the north pole is lying on the axis of the dipole. So putting theta equal to 0, we get from here Br, that is the magnetic field of the dipole at a distance r from it is mu0 m by 2 pi r cube. Now the north magnetic pole is approximately close to the geographic north pole. So we can take the distance of that north pole from the center of the earth, that is from the center of the dipole. The dipole is assumed to be at the center of the earth. That distance is equal to radius of the earth. So we get from this expression m is equal to 2 pi r cube br by mu 0. That is 2 pi r cube br by mu 0. 2 pi into r is radius of the earth into br is given. Then mu 0, we get it as 8.02 into 10 raised to 12 joule per Tesla. This is the magnitude of the dipole moment which is expected to be present at the center of the earth. Now the second question is, if we imagine the source of this field as a current ring, that is another possibility of the earth's magnetism. It is due to the current ring on the equator of the earth's metallic core. Core is present at a distance up to a distance of 3000 kilometers from the center of the earth. If we imagine this magnetism due to a current loop, then what will be the current required to pass? So if you imagine the current ring of radius b to produce the above field, we use the expression for the magnetic field on the z-axis of a current ring. It is Bz is equal to mu 0 I b square, where b is the radius of the loop, by 2 into z square plus b square raised to 3 by 2, where z is the distance of the point along the axis from the center of the ring. So we see that here z will be equal to r, because the north pole is at a distance of r from the center of the earth, and b is the radius of the circular loop. Now the current loop is circling around the center of the earth at a distance of about r by 2, which are already given, which can be taken as r by 2. B is equal to r by 2. It is 3000 kilometers. We can take it as r by 2, because we will calculate only approximate result. It is a possibility. So we can take b equal to r by 2. So we get Bz is equal to mu 0 I into b square, that is r by 2 square, by 2 into r square plus, that is z square, it becomes r square, plus b square becomes r by 2 whole square raised to 3 by 2. So we get r square by r cube becomes r, and the remaining we get mu 0 I by 5 raised to 3 by 2 r. Therefore I will be equal to 5 raised to 3 by 2 r into Bz divided by mu 0. So 5 raised to 3 by 2 r radius of the earth into Bz is 6.2 into raised to minus 5 divided by mu 0, 4 into raised to minus 7. So we get the current passing, the current required is 3.51 into 10 raised to 9 ampere. So these are the two possibilities for the magnetism of earth. One possibility is an assumption that a permanent dipole is present at the center of the earth. Another possibility is due to the circulation of current in the core of the earth. The third question, a cube of magnitude 5 centimeter on an edge is magnetized to saturation in a direction perpendicular to two of its faces. Find the magnitude of current in amperes of the ribbon of bound charge current that flows around the circuit consisting of the other four faces of the cube. The magnetization in the magnetite is 4.8 into 10 raised to 5 ampere per meter. Would the field of this cubical magnet seriously disturb a compass 2 meters away? That is the second question. Here we calculate the current and magnetic field of a uniformly magnetized cube. The side of the cube is 5 centimeter and magnetization is 4.8 into 10 raised to 5 ampere per meter. The surface bound current density is Kb equal to m cross n cap, and volume bound current density Jb will be equal to 0 because it is del cross m, and m is uniform here. So there is only surface bound current density. Now the current flows through the four sides as m cross n cap. It will be perpendicular to both the m and the n cap. So it flows through the four sides of the cube that wrap around the direction of magnetization. That is, the current will be curling around the magnetization. So the magnitude of this current density is m, because magnitude of Kb will be equal to magnitude of m. As m is uniform, we can safely take the magnitude as equal to magnitude of m, because n has unit vector. Is a unit vector, so magnitude is 1. The surface current is obtained. So the surface current density is m, and the surface current will be obtained by multiplying this surface current density with the width of the ribbon, which is the side of the cube, because a cube has the cube means it has the same length in all directions. So the width of the ribbon which is circling around the magnetization will be the length of the cube. So the current I is equal to surface current density into width of the path, that is equal to length of the cube A, that is equal to m into A. Now magnetization is 4.8 raised to 5 into 0.05. So the current passing through the surface is 2.4 into 10 raised to 4 ampere because of magnetization. This is the surface bound current density. Now the second question, does this field produced by this magnetized cube seriously disturb a compass placed at 2 meters away from the cube? For that, we should find the magnetic field produced by this cube at a distance of 2 meters from it. For that, first we calculate the total dipole moment of the cube. It will be equal to dipole moment per unit volume into volume, that is m a cube. That is 4.8 into 10 raised to 5 into 0.05 cube, that is 60 ampere meter square. Now the magnetic field due to this dipole along its axis at a distance r is as usual b is equal to mu 0 2m by 4 pi r cube. So it is 4 pi into 10 raised to minus 7 into 60 divided by 2. 2 and 2 cancel, so it becomes 2 here. So 2 pi r is 2 meter, 2 cube. It will be 1.5 into 10 raised to minus 6 Tesla. Now we see that the magnetic field of the earth is about 15 to 14 times larger than this value. So we do not expect the field of the cubical magnet to seriously disturb a compass 2 meters away. For example, the magnitude of horizontal component of earth at our place is 0.38 into 10 raised to minus 4 Tesla, which is about 3.8 into 10 raised to minus 5 Tesla. It is about 20 factor greater than this value. So the magnetic field at a distance of 2 meters from that cubical box is negligible with respect to when compared to the magnetic field of the earth. So there is no serious effect on the compass box. So thank you for watching this video.